In this video, we're going to talk about what derivatives tell us and how to graph functions. Specifically, we'll be talking about the first and second derivative tests for extrema and the second derivative test for concavity. We'll also be doing some curve sketching. Let's tell you the exact names of the objectives here. So we're going to find the intervals on which the function is increasing or decreasing. That'll be using the first derivative test. Use the first derivative test to locate critical points and locate local and absolute extrema. Sketch the graph of the function given properties of the function. Use the second derivative test to determine the concavity on intervals and find inflection points to tell where on what intervals the graph is concave up or down. Use the second derivative test to determine if critical points correspond to local maxima or minima. That's the second derivative test for extrema. And solve applications involving derivatives using the first and second derivative tests. That'll be curve sketching. So let's go ahead and talk about increasing and decreasing functions. Suppose f is defined on some interval I. We say f is increasing on I if f of x2 is greater than f of x1, for x2 greater than x1 if the slope is positive, right there. It's increasing if the slope is positive is what that's saying. We say it's decreasing on I if f of x2 is less than f of x1 for x2 greater than x1, saying that the slope is negative there. And we can measure the slope with the regular slope equation, the average rate of change, or we can use the derivative. So this will happen when f prime of x is greater than 0. This will happen when f prime of x is less than 0. Let's sketch a graph with the given information. So we have f prime of 0 is undefined. I'm going to assume that f of 0 is undefined since I don't have any points there. So it's just like so. And we want to be greater than 0 from negative infinity to 0. Let's put our fixed points on here. F, no fixed points. So we're going to be increasing on this interval. There we go. Then we're going to be decreasing on this interval. So until 4 out here. And then we are increasing from 4 to 6. It's going to be something that looks kind of cubic. And we're decreasing again. So this is at 4. This is at 6. Okay, so we have slope there, 6 to infinity, we're decreasing, and we'll just have something that looks kind of like that. You get the idea, though, that you've got a piece that looks cubic over here, just maybe a smooth curve like this over here that's rising to the right. Get this vertical asymptote going here, probably something like that. All right. Find the intervals for which this graph is increasing or decreasing and sketch the function. Use a sign diagram for f prime of x. So f prime of x is equal to 6x squared plus 6x. That's 6x times x plus 1. Set that equal to 0. 6x equals 0, or x plus 1 equals 0, x equals 0, or x equals -1. So our diagram here, we're going to put a number line. We're going to put -1 on the left, 0 on the right. We're going to test something from the interval of -infinity to -1, something from -1 to 0, something from 0 to infinity. So our f prime of x is equal to 6x times x plus 1. Let's try sticking in -2 for this interval right here. 6 times -2 times -2 plus 1 is equal to -12 times a -1 is a positive 12. That's greater than 0. So this is greater than 0. That means we're going to be increasing here. F prime of -1/2. 6 times -1/2 times -1/2 plus 1 equals -3 times positive 1/2 is a -3/2 is less than 0. So we have f prime of x greater than 0, f prime x less than 0 here. So we're decreasing. And f prime of 1, 6 times 1 times 1 plus 1 is 6 times 2 is a positive 12 is greater than 0. F prime of x is greater than 0, so we're increasing here. So increasing, then decreasing, then increasing. We're going to have a graph here that if I would stick those points in there, let's figure out x, f of x. F of x was equal to 2x cubed plus 3x squared plus 1. And I'm interested in -1 and 0. This can be 0, 1. My y-intercept, -1 is going to give me a -2 plus 3 plus 1. It's going to give me 2. Okay, so this is going to go up. Give me a local maximum there, then come down and give me a local minimum, then go back up forever, something like that. Should be what it looks like. So we're increasing from -infinity to -1, union from 0 to infinity. And we're decreasing from -1 to 0. We have a local maximum at -1, 2. We have a local min at 0, 1. Let's talk about what a critical point is, an interior point of an interior point C of the domain of F at which F prime of C is equal to 0 or F prime of C is undefined. It's called a critical point of F. If F prime of C is undefined, but C is in the domain of F, we have a cusp or sharp point, or we called that a corner on our graph before. For our first derivative test, we're going to assume that f is continuous on the interval, typically the domain of f that contains the critical point CF of C, and assume f is differentiable on that interval except possibly at C, because it's possible to have the critical number be where f of C, sorry, this is f prime. These are all primes. Assume f is differentiable. Yes. If f prime changes sign from positive to negative across x equals c, so we have on our sign chart that it goes from an interval where it goes positive to negative, and this is c right here, then there would be a local max at x equals c. If we have our sign chart and we go from negative to positive, there's a local min at x equals c. If we have our sign chart and two adjacent intervals do not change sign, there's no min or max at that place there, even though f prime of c is equal to 0. It's not a minimum or a maximum. F prime of c equals 0, no min or max. We'll talk more about why we get those points when we get to our second derivative test, but there's something called a point of inflection that we'll talk about later. All right. Let's go ahead and use the first derivative test here to state the intervals over which the function is increasing and decreasing, then classify any local minimums or maximums. F prime of x is 12x to the third minus 12x squared minus 12x plus 12. And we're going to set that equal to 0. Find our critical numbers. Going to factor 12 out. And then group x cubed minus x squared together. And I'll group a negative x plus 1 together. And this is going to be 12 times x squared times x minus 1 minus 1 times x minus 1 equals 0. 12 times x minus 1 times x squared minus 1. 12 times x plus 1 times x minus 1 squared. So x equals negative 1, multiplicity 1, x equals 1, multiplicity 2. If you remember about multiplicities from pre-calculus, it should help you figure out what's going to go on with our sign chart here, because we talked about that as far as x-intercepts, and these critical numbers act kind of like x-intercepts for the graph of the first derivative. So we're going to put negative 1 on here, positive 1 here. So because there's an odd multiplicity here, we should cross, meaning there should be a sign change. We should touch here, meaning that there should be no sign change. So on the negative side here, we should have a positive times a negative times a positive is a negative. When we put 0 in, we should have a positive times a positive times a positive is a positive. And we should, when we go to the right of 1, we should have a positive times a positive times a positive is a positive. This is decreasing, increasing, and increasing. Go ahead and stick some numbers in for yourself to prove that to yourself that those intervals are correct. So I should be decreasing, then increasing, then increasing. So there's a local min here. There's no min or max here. This is going to be what we call a point of inflection later. Let's just go ahead and stick some numbers in, though f prime of -2 is going to be, like I said, a positive times a negative times a positive is a negative, so it's less than 0. F prime of 0 was a positive times a positive times a positive is a positive that's greater than 0. This is increasing, decreasing. F prime of 2 was a positive times a positive times a positive is a positive that's greater than 0. It's increasing there. I'm only really paying attention to the signs now. I don't really care about the numbers. Increasing on the interval from -1 to 1. Decreasing on the interval from -infinity to -1, union 1 to infinity. No local max. Local min, which also happens to be an absolute min at -1. And if I stick -1 in, I get -12 minus 12 plus 12 plus 12. That's my derivative. 3 plus 4. Be careful to stick your x into your function f of x, not your f prime of x. You know that it's going to have a slope of 0 there. That's not what you're trying to find. So 3 plus 4 minus 6 minus 12 plus 1. All right, it's going to be all the positive numbers together. 8 minus 18 is a -10. There we go. Just while we have a second, let's review the steps here for the sign diagram that we're making, since I have some space here. So first, find critical numbers or points. Two, make a number line. Number line. And plot the critical points. Also include vertical asymptotes here. 3, evaluate the appropriate derivative. At the test points. Sorry, I skipped a step. Probably saying what test points. Pick test points for each interval. Are inside each interval or evaluate the appropriate derivative at the test points five. Draw necessary conclusions. If we're dealing with f prime of x, we're thinking about, is the function increasing, decreasing? Do we have min, max values? We're dealing with f double prime of x. We're thinking about points of inflection. And where's the graph concave up or concave down? Now we're going to follow up on the previous question. We're going to restrict the domain here. So we're still talking about f of x is equal to 3x to the fourth minus 4x to the third minus 6x squared plus 12x plus 1. Just we're going to restrict it from -3 to 1. Remember, our f prime of x here was 12x to the third minus 12x squared minus 12x plus 12. So this was 12 times x cubed minus x squared minus x plus 1. This was 12 times x squared times x minus 1 minus 1 times x minus 1, which gave me 12 times x minus 1 times x squared minus 1, which was 12 times x plus 1 times x minus 1 squared. And our first derivative test showed -1, 1, and this was negative, decreasing, then this was positive, positive, this was increasing, increasing. Now we're going to still look at that first derivative test, but we're also interested in not just these critical numbers at -1 and 1, but we're interested in the values at -3 and 1. 1 just so happens to be one of those critical numbers there. So we're going to find f of x now. F of x was equal to, it's up there, equals 3x to the fourth minus 4x to the third minus 6x squared plus 12x plus 1. So this is 9. So this is -3 times 81 minus 4 times negative 27 minus 6 times 9 plus 12 times negative 3 plus 1. If I figure all that out, that is going to be negative 243, 8 plus 108. Find the difference here. That's negative 135. And then minus 54 is minus 189. Then minus 60 is minus 249 plus 1 is a negative 248. Let's go with that. For negative 1, we get that this is going to be 3 plus 4 minus 6 minus 12 plus 1. So that's 1, 2. This is negative 10. And at 1, we get 3, negative 4, negative 6, positive 12, positive 1, 13, 7, 3, 3. I get 6. So the absolute min on that interval is there, and the absolute max on that interval is there, because this is the smallest y value on the interval, this is the biggest y value on the interval, because our minimums and maximums on a closed interval like that either have to happen at the endpoints or at the critical numbers between the endpoints. So I restrict that domain. I get so it was supposed to be 262. What did I do wrong? Oh, that's a positive, not a negative 3. That changed things a lot. So changes my answer. This is going to be 262. That makes that the absolute max for sure. And that makes this the absolute min for sure. All right. There we go. So let's make a little sketch here of this. We have negative 1, negative 10. Should be down here. And we should be going up to 1, 6. Like this. And kind of levels off at 1, 6. And then keeps right on going. So we have I guess I should make that point there before I go anywhere. 1, 6, and this is a point of inflection here. This is a local and absolute min here. And we're going to go through 0, 1. here. I need to grow really quickly, level out for a split second, change my concavity, and then keep right on going. Concave up. And that was increasing, decreasing rate. Be down here somewhere. Then turn, go back up here, and I'll have the point -3, 262 will be, I would have been growing really quickly. I just can't draw that very well and show it to you because the scale is so different, but we're way up here. It grows really quickly. All right, our second derivative test for concavity. Let f be differentiable on the open interval I if f double prime is increasing on I, then f is concave up on I. If f double prime, the second derivative, is decreasing on I, then f is concave down on I. F is continuous and f changes concavity at C, then f has an inflection point at C. So test for concavity, suppose that f double prime exists on open interval I. If f double prime is greater than 0 on I, then f is concave up on I. If f double prime is less than 0 on I, f is concave down on I. If C is a point on I with which f double prime changes sign at C, then f has a point of inflection at C. We want the concavity to change behavior. It's possible for it to come to a sharp point where the derivative and second derivative are going to be undefined, but the concavity may change there still. So watch out that this can include a cusp where f double prime of C is undefined. Make a sign diagram for f double prime of x, just like with f prime of x. Okay, just for determining concavity instead of increasing and decreasing. So in what intervals is f of x equals x cubed concave up or down? Let's just look at the graph for a second, and we're concave up from 0 to infinity. We're concave down from -infinity to 0. Concave up is where we're going to fill up the graph if we would pour water on it. Concave down is where the water is going to spill off of the graph if we put water on it. Let's do that mathematically now with calculus. We're going to get f prime is 3x squared, f double prime is 6x. We're going to set that equal to 0. X is going to be 0. We're going to make our chart here for f double prime. First, we'll make our graph for f prime. We'll say at 0, it'll be positive and positive. That gives us no info. We know it's increasing, and it's still increasing for f double prime. 0 is going to be a point of inflection, since it's a 0, the second derivative. And to the left here, we're concave down, and to the right, we're concave up. So we're going to have this type of a shape, and then this type of a shape. When we put them together, we get something that looks kind of cubic like that. It's just not as extreme here. That middle section, it's all pushed together, and it's concave down like that, and then concave up like that, and it looks kind of horizontal right there in the middle for a split second. All right, our second derivative test for local extrema. Suppose f double prime is continuous on an open interval containing a critical point C for which f prime of C is equal to 0. If f double prime of C is greater than 0, then f has a local minimum at C. Let's just take a look at that and see if we're on a concave down piece. We have to have a local max. We're on a concave up piece here, concave down piece here. Have a local min. And if we're equal to 0, then the test is inconclusive. We're on a piece that's like this at the point of inflection, or like this at the point of inflection. There's a point of inflection at x equals c there. Okay. We rarely use the second derivative test for concavity because we should already know from our sign chart from our first derivative test, if we do it out all the way, this just helps us skip that sign chart of the first derivative test if we're not asked to find intervals on which it's increasing and decreasing, and we're just asked to find the extrema and the points of inflection, then this would be beneficial to us to just do it this way. So we want to talk about concavity, points of inflection, and local minima and maxima. Notice it doesn't say anything about increasing and decreasing here. That's why we're going to use the second derivative test here. So y prime is going to be 4x to the third minus 12x squared. We're going to get our critical numbers by factoring out a 4x squared. That's going to give us an x minus 3. Our critical numbers are going to be negative 3. Sorry, positive 3 and 0. 0 has a multiplicity of 2, so I think that it's actually a point of inflection and not a minimum or maximum. And this has a multiplicity of 1. Let's come back here and take the derivative of this derivative. This is 12x squared minus 24x. We'll pull out a 12x here and get x minus 2. So we'll go straight to prime of x, f double prime of x, double prime of x. We'll go straight to plugging numbers in here. F double prime of 0 is going to be 0, which tells me that there's a point of inflection, no min or max at that point. F double prime of 3 is equal to 12 times 3 times 3 minus 2. 36 times 1 equals 36 is greater than 0. So there's a local min at x equals 3. If I want to find what that is, I have to go back to the original. F of 3 is equal to 81 minus 4 times 27, which is going to be 3 times 27 minus 4 times 27 is a negative 1 times 27 is a negative 27. So this is at 3, negative 27. So we can summarize here for this function, saying that it is, we weren't supposed to do the, we weren't supposed to talk about increasing or decreasing, so we won't do that. But it does have a point of inflection at 0, 0, 0. And we have the absolute minimum there. So there's also a point of inflection at 2. And if I plug 2 in here to the original, I get 16. And then 4 times 8 is 32. 16 minus 32 is going to be a negative 16. So that's my other point of inflection. Let's bring it all together and let's graph a function here. So guidelines for graphing, we're going to identify the domain, any intervals of interest. Question here about the domain, is it restricted? Treat endpoints carefully. Also, ask yourself if there are any undefined x values. That's going to be important. We're going to talk about asymptotes later in the process, but doesn't hurt to identify them right now while you are looking at the domain. Remember that if the function is even, it's going to have y-axis symmetry. That means that f of negative x is going to be equal to f of x. For example, you might want to think of the graph y equals x squared. This is optional. You don't need to do step 2, but it just helps you. This is going to be origin symmetry. Remember, that's f of negative x is equal to negative f of x. Think like y equals x cubed there. If it's not abundantly obvious to you that it has symmetry, just go ahead and skip that. It's not necessary. Find f prime and f double prime, and double check that you're using the correct derivative formulas for those. Find critical points and possible points of inflection. You're looking for where f prime of x equals 0, or f prime of, I'm going to call this c, not x. C is undefined, and C is in the domain of f For second derivative, you're looking for where f double prime of c equals 0, or f double prime of c is undefined. We have an example of this below. And use your first and second derivative test to analyze the function behavior, create sign charts, sign diagrams. I call it a sign chart. First derivative test. Will tell you intervals for which it's increasing and decreasing. Will also help you find max and min. Second derivative test will help you find concave up, concave down, and will help you find points of inflection. Use information from there to identify extrema, mins and maxes, and points of inflection, and locate all asymptotes, both horizontal. We want horizontal asymptotes, vertical asymptotes. We don't have horizontal, we might have slant asymptotes. We should never cross a vertical asymptote. So that's going to be a boundary on your first derivative test and second derivative test. Find the intercepts, the x-intercepts, and the y-intercepts that are fixed points on the graph, and choose an appropriate graphing window and sketch. So let's look at this. Here is saying just draw, for us, just draw the axes and label points that are important. For the graph's behavior. I'm not so worried about scale. Your teacher might be. If so, use a graphing utility to help you keep it to scale and choose an appropriate window for it. Let's look at this example here. We want to sketch f given the following information. First derivative is positive from negative infinity to 0, 4 to 6, and 6 to infinity. I think we did something like this before. F prime of x less than 0 for 0 to 4, and f prime of 0 is undefined. We definitely did this one before. F prime of 4 equals f prime of 6 equals 0. We're just coming back to that original example that we did. And there's nothing to tell me if I have a horizontal asymptote or anything like that. I graphed it like this with a vertical asymptote here. And then we came down to a minimum at 4. Then we went back up. We were increasing from 4 to 6. And then again from 6 to infinity, like so. This one might be a little bit different here. At 6, we were positive on both sides there, but it had to equal 0 in between. So there's no sign change. So there's a point of inflection there. Point of inflection there. And there's a minimum there because we go 4, we go from decreasing to increasing, decreasing to increasing. So there's a local min. All right. On to our final application here where we're going to sketch the graph of the following. So let's go ahead and let's find the domain of this by saying that x squared minus 1 can't be equal to 0, x plus 1, x minus 1 can't be equal to 0, x plus 1 can't be equal to 0, and x minus 1 can't be equal to 0, x can't be a negative 1, and x can't be 1. So our domain is going to be negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. I'm restricted to that domain. We're going to skip the second part where we look at symmetry because this just doesn't jump out at us. It's something that's going to be symmetric. So we're going to skip that because it was optional and not readily apparent. Okay. Let's find our first derivative here by using the quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And we're going to simplify that there. 30x to the fourth minus 30x squared minus 20x to the fourth over 10x squared minus 1 squared is 10x to the fourth minus 30x squared over x squared minus 1 squared. And I'm going to leave it just like that for a second. Now we want to find f double prime of x, so derivative of the top, 40x cubed minus 60x times the bottom, it's 1 squared, minus derivative of the bottom, minus 1 times 2x times the top, it's 30x squared, all over bottom squared, like that. And we'll have to, let's just go ahead and use some factoring here. And first things first, I see a common factor here that I'm going to subtract 1 of each of those out. I get 40x cubed minus 60x times x squared minus 1 minus 4x. This negative 2 times that 2 is a 4. 10x to the fourth minus 30x squared over x squared minus 1 to the third. So that gives me f double prime of x is equal to, and then this is 40x to the fifth minus 40x to the third minus 60x to the third plus 60x. And then we have minus 40x to the fifth plus 120x to the third, x squared minus 1 to the third, so f double prime of x equal to, that's 0. And then 120 minus 40 is 80. minus 60 is going to be 20 minus 60x, I'm sorry, plus 60x over x squared minus 1 to the third. All right. So that tells me now that I have f prime of x equals 0 when 10x to the fourth minus 30x squared equals 0. So I'm going to factor out a 10x squared and get x squared minus 3. That tells me that I'm interested when x equals 0 or x equals plus or minus root 3. Remember that 1 and -1 were never in the domain of my original. I'm going to be undefined at x equals plus or minus 1 because of vertical asymptotes that I'll need to account for on my first derivative test. So let me go ahead and put negative root 3, -1 is a vertical asymptote, 0, positive 1 is a vertical asymptote, positive root 3 is there for that sign chart. Now for f double prime of x equals 0, I'm interested in when 20x cubed plus 60x is equal to 0. Factor out 20x and get x squared plus 3. X squared plus 3 can never equal to 0. So I'm only interested in x equals 0. That tells me this is going to be a point of inflection here. Since it's a 0 of the second derivative, it's not going to be a minimum or a maximum value. Still going to be undefined at x equals plus or minus 1 that are not in the domain. So I have 0 here. I have -1. That's a vertical asymptote. And I have +1 that is a vertical asymptote. All right. Sign diagram here. So if I go ahead and I use my calculator and I stick in something, so this negative root 3 is about negative 1.7. This positive root 3 is about positive 1.7. So if I find f prime of -2, then I'm going to get something that is less than, sorry, greater than 0. And 0 there. And then if I stick in f prime of, say, -1.5, I get something that is less than 0. F prime of -1/2, say, -0.5. I'm going to get something that is going to be greater, sorry, less than 0 as well. Let's just check these all out up here with f prime. So sticking in something like a -2, that's positive, and this is positive. Sticking in something like a -1.5, that's positive. That's going to be negative. Sticking in something like a -0.5, this is positive. This is going to be negative. So yep, that's decreasing. Sticking in something like a positive 0.5, this is positive, and this is still negative. prime of 0.5 is still negative. So we're negative, negative, negative. This was positive. And then something like a 1.5 over here, positive, then that's going to be positive. No, that's still going to be negative. Sorry. And then on this side, when I go to the right of 1.7, this is going to be positive, and that's positive. This is positive. So f prime of, say, 2. This is going to be less than 0. This is greater than 0. So lots of negatives going on here. So lots of decreasing. We've got some asymptotes there. Let's go ahead and look at our graph from to the left of -1. I'm going to choose something like -2. And so if I stick in -2 here, this is positive, this is negative, this is concave down. Then between 1 and 0, something like a -1/2. This is negative, this is going to be positive. So this is still concave down. Then from 0 to 1, this switches to positive, this is concave up. And then on this side of 1, it's also going to be positive. This is going to be concave up over here as well. So oh, don't forget to account for the entire f double prime. I have x squared minus 1 over to the third power in the denominator. So yeah, I accounted for that. So we have this. Let's just deal with f double prime of x equals 20x times x squared plus 3 over x squared minus 1 to the third. So let me look once more here. This is always positive. That's going to be negative. That's going to be positive. That's concave down. This is going to be negative and negative. That's going to actually be positive. That's concave up. That makes more sense to me. Then this is also going to be concave. This is going to be concave down. Yes. And then this is going to be concave up. I should be changing concavity everywhere there because they're all odd multiplicities. Perfect. All right. That makes more sense to me. So let's sketch the graph here. And let's just summarize. We're going to be increasing on negative infinity to -3. Sorry, negative infinity to -√3 union √3 to infinity. We're going to be decreasing on negative root 3 to negative 1, union negative 1 to 0, union 0 to 1. Was that it? Union 1 to root 3. We have concave up on negative 1 to 0 and 1 to infinity. Concave down on negative infinity to negative 1. Union 0 to 1. We're going to have a local max at negative root 3. Going to have a local min at positive root 3. I still need to find my asymptotes here of my original. I'm going to go all the way back up here to say I have vertical asymptotes. X equals negative 1, x equals 1. I'm going to have a slant asymptote that I'm going to have to find by dividing x squared minus 1 into, is it 10 x cubed? It is 10x cubed plus 0x squared plus 0x plus 0. So this is 10x cubed minus 10x. Change my signs and add. 10x is smaller than that. This is my slant asymptote. Y equals 10x. Right? Axes here. X-intercept. At 0, 0. That's also going to be my y-intercept. So that's a fixed point. I've got a vertical asymptote here, and I've got a vertical asymptote over here. I have a slant asymptote. 1, 2, 3, 4, 5, 6, 7, 10. Like so. Let's get these boundaries defined here with these asymptotes, like so. So they're going to help determine where my graph resides, because it's going to reside in those regions in between, or to the left or to the right of those places. All right. So let's talk about end behavior of our graph as we approach our asymptotes from the left and the right to see what the limit is doing. So as I get close to negative 1 from the left, this is going to be positive down here. This is going to be negative up here. So I'm going to be going to negative infinity there. As I get close to negative 1 from the right, this is going to be negative, and this is going to be negative. So I'm going to be going to positive infinity here. As I get close to 1 from the left, this is going to be positive in the top and negative in the bottom. So that's going to go to negative infinity down here. As I get close to 1 from the right, it's be positive infinity over positive, or a positive over positive. It's going to positive infinity. So just my best guess of this sketch here, I'm going to be coming down here like so, kind of something that looks cubic in there. I'm going to be staying up here in this piece, and I get a local minimum here. I'm going to be down here, and I'm going to get a piece that's symmetric to that across the origin because this was odd, and has a local maximum. So this is an odd function, even though we didn't do number 2. So everything that's up here has to be down there. That's why this piece is concave up and this piece is concave down. This piece is concave down. This piece is concave up. So that matches with this that says down, up, down, up, down, up, down, up. It's increasing, then decreasing, then decreasing, then decreasing, then decreasing, then increasing. That matches what was here: increasing, decreasing, 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 increasing, increasing, decreasing, 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 increasing. And this is at root 3 something. This is at negative root 3 something. I can stick that in to my original f of x and see what would be going on with that. I'm not really that interested in that exact number right off the top of my head. If you are, go ahead and stick it into your calculator, get a decimal approximation, and check and see if that's what your calculator says for the extreme values. But there you go. That is a good practice problem for curve sketching. And we'll leave it there. We'll come back next time and we will start to talk about optimization. You're going to want to have the geometry formulas handy for that. We're going to be talking not just about 2-dimensional geometric figures, but 3-dimensional geometric figures, especially rectangular prisms. We might be talking about right circular cones, right circular cylinders, and we'll be talking about spheres for sure, maybe some other geometric figures as well. We'll be talking about circles, we'll be talking about squares, we'll be talking about cubes, we'll be talking about triangles, right triangles, possibly, all kinds of things. So come on back and have your geometry supplement handout with those formulas handy for you. And we'll talk about optimization next time.